Okay, so I suggest that we start once again. Welcome to this webinar co-hosted by Phimeca and Simvia. I'm Maxime Guéguin, I'm the CTO of Simvia. As you may know, we have as a mission, as a subsidiary of EDF, we animate the community around open source simulation codes, and that's one of the reasons why we try to have some tutorials and some webinar about these tools. The idea is always to highlight the capabilities of these tools, and most of them are developed by EDF. So it's a main mission for us. Today we will listen to a great work made by Mohamed and Phimeca. They have great expertise in Persalys and Codaster, and we will have a very nice demonstration of the capabilities of these codes. During this webinar, do not forget to ask some questions. We will have, let's say, 10 minutes for questions at the end of the webinar. So do not hesitate when Mohamed is presenting the work to ask some question, and we will try to answer this at the end of the webinar. Mohamed will do a presentation of the work during about 30 minutes. So yeah, for me it's a great pleasure today to introduce to you Mohamed. Mohamed holds 2 master degrees, one in mechanical design and the other one in computational mechanics. He works for Phimeca and has 8 years of experience in numerical simulation, and his work is focused on the behavior of materials, finite element modeling, and the automatization of simulation processes, and that will be the topic of this webinar. So once again, welcome Mohamed, and the stage is yours.
Thank you. Thank you, Maxime, for the great introduction. You have definitely given me much more credit than I really deserve. Hello, everyone. Thank you for joining this session. So the idea today is to walk you through the workflow that we have followed in order to automate a simulation process and then be able to create an optimization study using open source tools developed or co-developed by EDF. So we will begin by briefly introducing the tools that we have used, that are Salome, Codaster, and Persalys. After that, we will explain the context of the study before diving deeper into the technical aspects of the presentation. The technical part will be actually split into 2 sections. The first section is about the parametric simulation using Salome and Codaster. And the second one focuses on the optimization phase that will be done with and that have been done with Persalys, in which we will cover the creation of a design of experiments, the construction of a meta model, and finally the optimization itself. And by the end, I will wrap up with an overall synthesis of the whole workflow. All right, so the first tool that we're going to present is actually Salome. So Salome is an open source platform dedicated for pre and post-processing operations for different types of numerical simulations. It actually acts as a container, as you can see in this graphic here. It actually brings together the tools that are needed, for instance, here for the creation of geometry, the construction of mesh, and also results visualization. It also enables, and it actually gives the possibility to integrate different types of solvers, as you can see here, depending on the physics of your problem. In our case, we're dealing with a structural mechanic problem. So in that case, we are using Codaster. That actually brings us to the next slide. So about Codaster. So Codaster is an open source, also finite element solver for different types of simulations, whether it was static, dynamic, model analysis, or even thermal analysis. It actually enables the fact that you can deal with different materials, such as metals, concrete, or soils. It also supports different types of finite elements, from beams, plates to complete 3D models. One of the strengths of Codester is the fact that it is actually continuously validated and tested through thousands of test cases, industrial test cases, and also it provides the scripting feature to make it easier to automate and reproduce analysis workflows. Last but not least, Codester is also able to provide HPC features, which makes it very suitable for large and complex studies. The third tool is Persalys. So Persalys is now integrated into Salome, and it is also an open source graphical user interface that is dedicated to the treatment of uncertainties. It also enables to create mathematical models, whether they are analytical or coupled with external models. And this is actually the case that we're going to see today, this case here. It also gives the possibility to analyze the variability of your parameters and also statistically analyze your measuring data. All right, so once we have presented all the tools that we have used, let's go see the context of our study. So this is actually the valve we are dealing with here. It is a part of a fluid control system. It is also subjected to internal pressure, and the goal here is actually to reduce the overall mass with always with respecting the maximum allowable limit in terms of stresses. Okay, let's now go see the technical part. The first part is about Salome and Codester. So the first module that we are using here is actually a shaper that enables to create geometries. What you see at the center here is the final form of our geometry that we created both with the graphical and the scripting node of shaper. What you see at the right-hand side here is small snippets of the whole script that created this valve. Here is a parameter that actually controls the fillet radius here. Here we are controlling the external valve radius, and at the end we are controlling the number and the size of these studs here. On the left-hand side, you can see different configurations that are produced with this script. So here we have a bigger fillet radius. Here we have a wider external radius of the valve. And the third configuration is actually a valve with less number of studs and a different size of the holes here. Let's now switch into the real interface actually and see how things work here in action. So this is the interface of the shaper module within the Salome platform. For those who are not familiar with Shaper, you have actually here all the toolbars needed to create either sketches here or to perform operations to generate 2D or 3D models, just as like you with the toolbars that you can find in any other CAD tool. On the left-hand side here, you have different items related to the creation of geometry. Maybe the main ones are here, the list of the parameters that are needed for the creation of our geometry. This is actually optional, but very important here for our study. So here you find all the parameters that we used. And then you have the construction tree here that actually gives you all the operations that have been performed in order to achieve this kind of geometry. We could maybe isolate this one. Maybe the first sketch actually here, if you click on show only, this is actually a sketch that what you see here is actually the generatrix of the upper part of the valve. So it is done first in a 2D sketch, and then that sketch is actually used in here in this operation, this revolution operation. We open it here. You can see that the first argument is actually the sketch that we just seen, and the second one is actually the revolving axis. And with these two arguments, we're able to generate a 3D part like this. So following this same logic, we're able to create the valve that you can see here. Also, the thing is that you can create this kind of geometry and more complex ones, either going through the graphical user interface or also by scripting. The good news is that Salome already provides you with a script that actually stores all the actions that you have performed here. In order to get it, you go to File, Dump Study, and you can here start it. I've already done that, so let's go and see what it actually looks like. So this is actually the dump file that is generated automatically by Salome. You can see here the first part is about importing the modules and all the functions that are needed. Can you still hear me? Because I'm having some troubles in my sound.
It's perfect, Mohamed.
It's perfect. Okay. Okay. Okay, so let's carry on. I was saying that the first part is actually about the importing all the functions and modules that are needed. And then we carry on with different operations. For instance, you have here all the parameters that you have introduced, sorry. And then you have here, for example, the creation of a sketch, and then all the operations that are performed within that sketch. One interesting point that I would like to see with you here is the group creation, actually. So let's go over there to that section. Okay, so for example, for the creation of groups related to studs, as you can see here, we are going to have a same pattern that repeats itself for the creation of the stud 1, and then stud 2, and stud 3, and so on. So this clear pattern is actually something that could be used later to be put within a for loop, actually, as the number of studs is a variable that we already know. So we could imagine that we have a for loop here that automates the creation of this kind of groups. So this is just an example for things that you could do through the script. Okay, let's go back to the presentation. So we are done with the geometry parts. We can move on to the next stage, which is the creation of the mesh. So here you have the final version of the mesh. We mostly meshed with tetrahedral elements, except for this zone here, where we expect the highest stresses actually. So in this part, we have decided to mesh it with hexahedral elements for more accuracy. Also, the bolts are modeled with beam elements, even if you cannot really see them here. Trust me on this, there are really beam elements connecting holes on either sides. Okay, so that brings us to the next step of the study. So once we have generated the geometry and mesh, we can move on to Cadaster. Actually, the Cadaster needs two things. It needs a mesh and a comment file. So to generate the comment file, one of the ways we do it now these days is actually going through the Aster study module, which is one of the Salome Mecha modules. I'd rather go directly to the interface so we can see things in action. Sorry. Yeah, so this is the Aster study interface. What you might notice is this toolbar here with all the buttons. Actually, they are mapping out all the whole workflow within Cadaster. So it goes from the mesh creation or the mesh reading until the outputs here. So if you're not familiar with Cadaster, you can just go along with this whole workflow in order to write your command file. So for instance, here under the mesh button, you have all the commands that are related to meshing. So for instance, you have here lire-maillage, which corresponds to mesh read, and then modi-maillage that corresponds to modify a mesh, and so on and so forth. The next step is actually to define the finite element model. And here you have all the commands that are related to this feature. Also, when it comes to materials, you have the possibility to define a material and then affect it to different regions of your model. You have also different commands depending on the type of materials you're dealing with. For instance, here you have composites. You could also have concrete here, and so on. The next important command maybe is this part where you have the possibility to define boundary conditions and loads depending on the physics of your problem. Once again, here you have Meca operators that would help you impose boundary conditions of mechanical type. Also, you have thermal here and other physics that are included here. The pre-analysis, if ever needed, for example, when you're dealing with the model analysis, one important operation is actually the assembly of the stiffness matrix that is done with this operator. Next is actually the analysis, and here you have all types of solvers that are available within Codasters. So you have solvers for dynamics, for statics, thermics, that are all available here. And after that, you have the post-processing for processing all your results. Actually, you have a separate section for fracture and fatigue with dedicated operators here. And finally, the output, where you can actually write your results into different types of files and formats. So for the current study, we actually use this workflow, in order to generate our comment files. So as you can see here, under the mesh item here, you have the command that is deepening, that is actually written here, modifiage, which will actually modify the mesh in order to give a different orientation for some of the faces we need here. And you have all those commands here, boundary conditions, for instance, and so on. One particular point here is that you can switch from this graphic mode that helps you actually to generate all the commands into a text mode where you can see the results of what you actually have written in terms of command file. So this is, the command file here that has been generated by Aster Study through the graphic user interface that you have used. So this is actually the whole command file. It is a text and the Python file actually that you could directly modify here manually. You can get rid of some of its parts. You can put on for loops, for example. Anything that has to do with a Python command could be done. All right, so this is how we construct the command file. Let's go back to the presentation. So here we have summarized the whole construction tree that we've seen previously, and here we have gathered all the hypotheses that we have for our computation. So the boards are actually modeled using PUDE beam elements, which are Euler beam elements that are available within Codasters. We have a special connection between the holes and those beams, and also in terms of loadings, we have a contact between the head and the body of the valve. We have the tension of the bolts that is modeled actually by the bolts displacement. We have the inside pressure that is applied into the valve, and also a background effect. So yeah. I think we can move on to the last step before we are able to go to Persalys. So we have seen actually how to generate within Salome the DAM file. So this is actually the original DAM file that is generated by Salome. We will need to perform some adjustments in order for it to be actually completely operational under Persalys. So the first thing that we have to do is actually to embed the whole script within a Python function, as you can see here. So we have just put the script into here. The function name is in here, and you have the whole signature with the arguments that are needed for the generation of the mesh. So this is actually the first step. It also includes the fact that we are actually changing the hard-coded values into real variables that could be controlled with this function. So this is the first step, and the second step is just actually adding these placeholders, these tokens here, for Persalys to recognize the variables that have to be varied for different types of studies with Persalys. So going from here to here is just adding these placeholders here. And doing this for the mesh generation script, and we are doing the same thing, the same logic is applied to the command file within Cadaster. And as soon as we have these two files, we will be ready to go to Persalys and perform our optimization study. So this is actually the end of the first part of the technical presentation. The second part is where we're going to focus on Persalys and how we can achieve the optimization study. So the workflow is actually to first create the design of experiments, then construct a meta model using that design of experiments, and from that we're able to perform the optimization study. Okay, actually the next slides are here to summarize the different steps that you need to perform within Persalys. I'd rather switch directly to the interface in order to see things in action. Persalys is here. Okay, so when you first open Persalys, this is what you actually get. Here are all the models that are available within Persalys. The one we are interested with here is the coupling model here, because it is actually the one that enables the execution of external codes within Persalys, which is the case for us here, as we are using Salome and Cadaster, Salome for the generation of the mesh, and Cadaster for the execution of for running the finite element simulation. So as soon as you click here, it will generate the first part here, which is the physical model. Actually, the work that will be done within Persalys is split into two parts. The first one is using the physical model in order to generate the design of experiment and then build the meta model from that design of experiment. Once the meta model is actually built, we are going to use it in the second phase to generate actually the optimization. So the first step is the use of the physical model. As soon as you click here, you get this coupling model and you get this definition tree. For our case, the path to follow is this one actually. So I'm going to create the design of experiment, evaluate it, construct, create a meta model using that design of experiment, and then export the meta model to be used later. Okay, so for the definition's sake here, we have to define the chaining of the commands we want Persalys to execute. The first command is actually to launch Salome with this script that would generate the mesh. This script is actually generated by Persalys itself using the template that we have seen previously. So Persalys will use this template and it will affect and will replace the placeholders with real values. And once Persalys has done that, it will create this file that will be finally executed here. So we're going to execute this file, and as an output, we are expecting to have this file output mesh, in which we will have the value of the mass, which is our first output. This is for the first command. The second command is actually about running Cadaster. So one way to do it in the command line is through the run aster. So we are going to use run aster, and run aster needs an export file here. So I'm aware that we did not talk about the export file, but it is actually just a file that gives the location of the command and the mesh file. It also controls other parameters for running the simulation, HPC parameters and other stuff. But the most important thing is that it gives the location of the command file to be used. So actually, Persalys, after executing the first command, will execute this second one by calling the parametric export file. And within this parametric export file, we're going to actually use the command file. The command file, as it was the case for the first one, the Python file, we are going to give Persalys a template file with the placeholders to be replaced with real values that Persalys will determine. And it will create that way a new command file. This command file is called upon by the export file, and we're able to execute the whole study with Cadaster. Afterwards, we will have an output here, an output file, which is the output aster.txt, in which we will find the von Mises value that we need for our optimization study. And the third command here is actually optional, but very important here. We want actually to get rid of the mesh once we have performed the study and Persalys has extracted, the values that are needed for the optimization. So once that is done, we want to get rid of the mesh because otherwise we would have plenty of them and it would actually be a memory problem. So this is more of a memory management command. Okay, so this is for the commands to be executed. The second thing is actually the probabilistic model. And here we have listed all the variables that will be controlled by Persalys. If you don't have, like it was the case for us actually, you don't have any other information about your variable distribution, default distribution is actually the uniform law, as you can see here. And you have to go, to give an upper and you have to give the bounds actually of the variable within it could be varied. So we have here, we're giving the lower and the upper bounds. Once we have defined our commands and the probabilistic model, we are able to actually create the design of experiment, which has been done here. So this is actually the way to do it. This oh, if oh sorry it's on here. So yeah, all that we need here is to give a name for the design of experiments, select our outputs, and we are done with this. And then Persalys is able to generate this design of experiments. And then we have multiple outputs here. One of them is actually this table that actually maps out all the simulations that have been performed by Persalys, commanded driven by Persalys and performed by Salome and Colaster. You have here are for each one of the experiments the values of the inputs and the outputs that are mass and van Mises. So in order to have a complete design of experiments, we have performed 100 simulations here in order to have all this. Okay, so once we have generated the design of experiments, Persalys is able to generate a meta model over it. So this is actually the result, the meta model. This is the way to generate it. So if you click on meta model, you are able to select the design of experiments from which you want to start, and the outputs that are needed for the study. And then here you have three methods depending on the distribution of your data. In our case, the region is the one that fits better. So this is actually the first step. In the second step, you have other parameters that could be configured here for your region parameters. So we are going by the default ones here. And the final one is also concerning the Q2 factor that is used for the validation of the region model. So in here again, we are going by the default values. So click on finish and then run, and at that time, Persalys will be able to generate the meta model. Okay, so once the meta model is generated and we are satisfied with, we can actually convert it to a physical model. In here, it's not possible because I did not run it. We don't have the time to do it here. But once it is done and validated, we click here and we go by convert meta model into physical model. And that actually creates a meta model here that could be used later for the optimization. So we get here, this is our meta model. We are here again, so with the model definition, and what we want to do this time is actually go by the optimization. So once you click on optimization, you obtain this here. So this is actually the result of the optimization with the optimum values. And the way to do it is actually by clicking on optimization, and you get this window here. So you have here listed all the variables. You can select all of them or just certain ones. If you want to optimize just some of them. One important point here is the starting point, because the better the first guess, the better the result. So for this, actually, what we have the habit to do, Phimeca, is actually go back to the evaluation of the design of experiments. Note the mass column here, and as you can see, we have all the results here through the mass. We are going to select the least mass that we have here, sorry, and that actually also respects the condition for the von Mises that we want, which is actually 1.5 to the power of 8. So this line actually respects that condition and gives the smallest amount of the mass. So one thing that we do is actually to manually copy these values of the inputs and give them as a starting point for the optimization. So this is about it for the optimization, I think. Next thing that we give here is actually the threshold for von Mises variable of the constraint variable that we have. And then the final here also for we have the possibility to select the method that the Persalys is going to use for the optimization. We have tried some of them. If you have any doubts or if you want some documentation, we have here available a documentation for each one of the methods. If I actually click here, I get directly the link to the documentation within the open terms, and it gives you an overall description of the method and all the attributes and methods that are available within it. Okay. And finally, here we are specifying that the optimization problem is a minimization problem, actually, because we want to minimize the upper mass of our valve, and the rest of the default parameters could be changed manually, but we strongly recommend to stay with these here. Okay, once you have finished the configuration, you click on Run, and Persalys actually performs the optimization. You have here a summary of all the parameters that you have defined. For instance, here the method that has been used, the threshold for the constraint, the starting points, and the bounds also for all the parameters. Okay, we go back to the presentation. So as I said earlier, all the steps are summarized here within these slides. Actually, we can see here the design of experiments with a scatter plot of all the simulations that have been performed, and the choice of the region model with the validation parts, and also the validation parameter that is Q2 here with a high value. And finally, here's the result of the optimization. So here are the nominal values of our variables, and here are the optimal values of those same variables with transformation in the mass. So we have a lesser mass here with these operations. Okay, so that brings us down to the last slide of the presentation, which is the synthesis of the whole workflow. So here, the starting point is actually Persalys, which is, as you have seen it, the driver of all the operations. The idea is actually in the first step to use the physical model in order to create design of experiments. So as long as this design of experiment is not completed, Persalys would generate new inputs, gives them to Salome in order to build a new mesh, and gives those inputs also to Colossus that would compute using the mesh and the inputs from Persalys. This simulation returns the outputs until we are finished with the design of experiments. Once it is done, we go and ask Persalys to build a meta model. As soon as we have that meta model, we are going to use it in order to search for the optimum. As long as it is not reached, Persalys will generate new inputs, gives them to the meta model that will return the outputs, and we're going to repeat this loop until we get to the optimum. So this is actually a simple flow chart to simplify what we have seen here, the use of the different tools, and how we could get from a simple mechanical simulation to an optimization using Persalys, Salome, and Elastic. So I think that's it for me. Thank you for listening. If you have any questions, I think you have the chat to do that. And back to you, Maxime.
Yes, Exactly. Thank you very much, Mohamed. It was amazing. As Mohamed said, you may ask your questions in the Q&A section. We have a conversation. I try to copy paste what is happening in the conversation, but do not hesitate if you have any question, and we will take a few minutes about this. Just in this process, what I wanted to mention about Codaster is the fact that you will need in this process to do many computation with Codaster. So maybe you want to parallelize this, and as Mohamed said, there are strong capabilities of Codaster about this, due to the fact that EDF is working on this since decades. And the idea mainly is to use the partitioning of the mesh. So we have done some benchmark. I'm not sure that it will be that clear here, but you have a version that you can download, which is based on OpenMP protocol, but you also may activate the MPI protocols, and that's what we do at Simvia. So maybe on the next slide we will see this. Sorry, it's not that clear. I don't know what you have the video, but
yeah,
you may want to hide this. So yeah, we have done many benchmarks about this protocols and the parallelization. As you can see on the right of this slide, there is differences between doing the OpenMP protocol only or using the MPI process. So if you are interested in this, do not hesitate to contact us. We can help to have the better installation of Codaster to run this really faster. So we will in few weeks try to do some publication about this performance of Codaster. But if you have some questions about this, do not hesitate. So to conclude, before we answer to the many questions that we have, we tried today, and Mohamed is a good example on what can we do with these codes. So it's also an opportunity for us to announce a partnership between Phimeca and Simvia. We have, I think, some strengths that can be helpful for industrial needs, for the study part, but also for the, let's say, the part dedicated to the informatic pipeline. So if you want to share with us about this, you can contact us directly. And also, if you want to showcase what you can do with the open source codes developed by Simvia, do not hesitate to contact us. So once again, thank you, Mohamed. It was amazing. And I think now we will take 5 minutes to answer the questions that we have. So as I said, some of them went from the conversation, other one from Q&A. Maybe just the first one is for you, Mohamed, obviously. So it's related to Shaper. If you want to load a step file in Shaper, can you still associate some dimension as a parameter of your study if you don't start from scratch, let's say?
So basically, if I understand well the question, you are importing a step file to Shaper, which has some dimension to it, and you want to modify it. Is that the question?
Yeah, I believe it is. It's from Sylvain, yes.
Okay, so one of the things that could be done actually is to import it directly within Shaper. So you have a direct feature to do that. You also have the possibility to import other formats other than steps, the 3D formats that are used widely. And once it is in the Shaper module, you are able to apply all the operations that are available within Shaper. So this is something that is done continuously by us at Phimeca and by other users. But yeah, something that works well within Shaper. I don't know if that actually answers the question. It is supported by Shaper. no matter the dimension that you give for your stepwise.
Okay, great. There are some other questions about Persalys, but I think that Usama from Phimeca gave some answers about the fact that for each run that you will launch with Persalys, you need to have, let's say, a Python file and a COM file for each point of your design of experiments. So I think that's the case, and maybe you need to clean a little bit when you are starting to work with this. Another question was about the fact that you use Shaper, the Shaper module, to do the geometry instead of the Geom module. So what is the reason about this choice?
Yeah, that's a very good question, actually. The Geom module actually is the historical module for geometry creation within Salome, and I'm talking under the control of some experts that we have today of Salome. But Shaper is actually the tool to come for the Salome platform in terms of geometry construction. So it has new features that are developed continuously. Also, the philosophy and the spirit of the creation of geometry is different from Geom, because you find actually that logic of creating a sketch in 2D and then using all the operations that are available to create 2D or 3D models. So that new way is actually more flexible to create more complicated, more complex geometries. So it is, yeah, that's the reason why.
Okay, great. Thank you. So all the mics are closed, so you can't ask some question by voice, but if you still have some, we can take another one. Just one question was about this webinar, so we'll make sure that every people that came to the webinar, or your colleague, if they can't join us today, we have a recording of this webinar, so we will share obviously with you what is happening. Yeah, because we don't have any more questions, just to let you know that what Mohamed showcased today will be the object of videos, and we will share this on our YouTube channels. So stay tuned on LinkedIn and other way to communicate, to be able to do what Mohamed demonstrate with really a strong expertise, and to know how to take this step in your own studies. So stay tuned. Thanks again for joining us, and once again, Mohamed, many congrats about what you have done, and thank you for watching. We will end this webinar, and we will be more than happy to take contact with you if you have any questions. Goodbye.